Welcome to the listeners. Now we can see about the types of motion which is related to our mechanics units. Not all the types of motion. We are concentrating here only two types of motion. One is the translational motion, another one is the rotational motion. First one, the translational motion. So in translational motion, it occurs when an object moves from one point to another in a straight line or a curved path without rotating. According to our definition, in translation motion, a body moves in a straight line, in which case all the constituent particles move along parallel straight lines and will undergo equal displacements in equal intervals of time. That is, all the particles in the body will have same velocity and acceleration. So here you can see some of the examples. The first one is a movement of a car or bus which is moving in a straight line, but all the particles will undergo equal displacement. Example, the car front part and the car last part, everything will be in a same movement. If the front part particle is moving with a particular velocity, the last point of the car back body also moving in the same velocity, and both the particles will cover the same distance only. So this is the example for translation motion. So what are the characteristics we are going to discuss here? That means there is a change in position. What happens to the change in position? Here there is no rotation. The motion will be a uniform or a accelerated motion. So both the type of motion will be under a translational motion. The next example is a coin moving over a carom board. So all the coins can be equally displaced, but everything doesn't have any rotation. So they are moving in a straight line only. Next, coming to the third one, an apple falling from a tree. Already we know this is the best example from the basic of physics. The last one, the cat walking. It also moving in the cat front part, front leg, and the last leg, back leg will be moving in the same speed. Both are covered with the same equal displacement. So these are the examples for a translational motion. Coming to the next one, that is a rotational motion. In rotational motion, a body moves about a fixed axis and each particle describes concentric circles about that axis. Though different particles at different points of the body will have different linear velocities, but they will have a same angular velocity. That means the rotational motion occurs when an object rotates around a fixed axis, changing its angular position only. So here the main characteristic we are discussing is rotation around a fixed axis. What happens in a change in angular position? Then what types of motion having here, that is a uniform or accelerated rotation will be takes place here. Not a motion. This motion maybe call it as a rotation. That is a uniform rotation, or we can call it as a accelerated rotation. Example, number of examples are there. One is a spinning top, another one is a rotating wheel, then earth rotation on its axis, gear system in a car. Here also another some examples which were showing in a screen. There is the first one is a motion of a door about its hinges, then wheels, pulleys in vehicles and machineries, rotation of plates in a fan, rotation of CD, DVD in CPU, etc. Next, according to this rotational motion, we can move into the next topic, that is the rigid body. So we have to know about what is rigid body. It has a definite shape and size and does not change due to external force. In other words, rigid body can be defined as an extended object in which the distance between particles is not altered during its motion. See the examples which was explaining you as a clear one. Next one, coming to the rotational motion. A rotational motion in a rigid body may be considered as a stationary motion, and here the rotation is caused by a couple acting on the body. Its state can be changed only by applying a couple or a set of couples. See the figure? The figure having a three axis, that is the body will be considered in a three-dimensional position. You have to consider x, y, z axis and its origin O. In this body, consider any 2 points, two particles, say P1 and P2. which revolves in a circular path. Here the rotational axis will be concentrated along the y-axis with the angular velocity omega. Here, the center for the each particles lie on OY and the radius of the circle is AP1 and BP2 will be equal to perpendicular distance from the axis OY. Then we know the rotational motion, though the particles will have different linear velocity, they will have a same angular velocity. Therefore, all the particles will rotate through an angle d theta in a small time interval dt. So here we can coming to the definition, basic definition, that is angular velocity omega can be written as d omega by dt. Corresponding to the angular acceleration, we know the alpha value, that is alpha is equal to rate of change of angular velocity, that is d omega by dt. Next one, coming to the rotational kinematics. So after all the types of motion and rotational bodies, we have to move to the rotational kinematics. That is, it describes the interrelationship between the angular displacement, theta, angular velocity, omega, and angular acceleration, alpha, with respect to the time. It describes the rotational motion of the particle without considering the mass or force that affect the rotation. See the figure, it is a cycle wheel. It have a center of axis in the center point. That is the axis of rotation will be passing through the center point of the wheel. It is rotating in a clockwise direction. So here the kinematics of rotational motion for constant angular acceleration with respect to an axis of rotation is analog to kinematics of linear motion. Next, we have to make a comparison between a linear and rotational motion. In linear motion, the velocity can be described with the symbol v, and in rotational motion, the velocity can be angular velocity can be written by the symbol omega. The suffix f indicates the final velocity, and the suffix vi indicates the initial velocity. So here, initial velocity, we know the Newton's equations of motion. There is a three basic equation. The first equation is equal to V is equal to U plus AT. We studied in our lower classes, but here the U is called as the initial velocity. According to our understand, the U can be replaced with the symbol VI, that is this one. So instead of U, we can return it as a VI, that is initial velocity, and the acceleration indicates A. But coming to the rotational motion, the angular velocity was described with the symbol omega f, that is final angular velocity, and omega I indicates the initial angular velocity. And here the angular acceleration can be represented by the symbol alpha. So wherever Vf having here, it can be replaced with omega, that is angular velocity omega, linear velocity v. Coming to the next equation of motion, S is equal to vt plus half, that is ut plus half at square. We studied in our half at square in our lower classes. This here the S indicates the displacement, and vi indicates the initial velocity. Coming to the rotational motion, this displacement S can be replaced by the symbol theta, and initial linear velocity can be replaced by the initial angular velocity omega I, and here it is alpha. So what's the equation here? S is equal to VIT plus half AT square. Here theta is equal to omega IT plus half alpha T square. Coming to the third equation of motion, Vf square is equal to Vi square plus 2As. Vf means final velocity, Vi means initial velocity. Then coming to the rotational motion, it can be replaced as the omega f square is equal to omega I square plus 2 alpha theta. Okay. So I think you can understand the difference between linear, how to write the equations of motion in linear motion and rotational motion. So we can start our equation here. Rotation of rigid bodies. Here we know the kinetic energy of rotational bodies. Kinetic energy of a kinetic energy equation of a rotational body, that is the same figure which can be seen in the previous one. This is a body. This is the body which have number of n number of particles. Take any two, m1 and m1, m2 and mi. Here this is a mi. This is mi. For I number of particles, we are taking this one, m1. This m1 point can be rotational kinetic energy. So now only we can see this one. M1 and M2 was the particles which we consider in the n number of particles. So this M1 can be placed at a distance r1 from the axis of rotation. This x dash is the axis of rotation with which is rotated with angular velocity omega. Second particle m2 is lying at the distance from the axis of rotation is r2. So the relation between linear velocity and angular velocity can be written as v is equal to omega r. Omega is a angular velocity and v is a linear velocity. So for the particle m1, this particle is rotating above the axis of axis x dash. So with the velocity v1 is equal to omega r1. Then comparing to the second one that have rotated along the axis, that is v2 is equal to omega r2. So we are coming to the derivation part. Therefore, the velocity v1, v2 and vi be a linear velocities of the particles of masses m1, m2 and mi rotating above the axis of rotation at a distance r1, r2, ra respectively. So for the first particle, the kinetic energy can be written as half m1 v1 square. For the second particle, it can be written as a half m2 v2 square. So for the ith particle, we can return it as a half mi vi square. So the total energy can be written as a m1 plus m2 plus and so on. So therefore, total kinetic energy half m1 v1 square plus half m2 v2 square plus and so on, half mi vi square. Let it be equation number 1. But we know the relation between v1 and r1 omega, that is relation between v and omega, that is linear velocity and angular velocity, is v1 is equal to r1 omega for the particle m1 and v2 is equal to r2 omega for the particle m2, and for the mi particle vi is equal to ri omega. So now the equation 1 becomes, so we have to replace the v1 value in this equation and v2 value in this equation. So now what happens? Total kinetic energy is half m1, instead of v1 we have to put r1 omega the whole square. So it can be written as the r1 square omega square plus half m2 r2 square omega square plus and so on. And finally half mi ri square omega square. So the total kinetic energy can be written as we can take it as a sum of all the things. Here the common thing is 1 by 2, but m1 to mi can be written as mi, and r1 to ri can be r1 square to ri square can be written as ri square. The another one common thing is the omega square. For the rotational body, the angular velocity does not changes, but which will change? Linear velocity becomes change because the have only one axis of rotation. So the total number of particles in the system can be rotated only by the rotational axis. But there is no change in angular velocity, but there is a change in linear velocity. So now we can return it as a total kinetic energy half I omega square. The bracketed term summation I mi ri square can be written with the word I. It is called as a moment of inertia. So now we can came to the definition of moment of inertia, that is summation I mi r square. Mi means mass, Ri means the distance. So we can define the moment of inertia, that is sum of the product of the mass in and square of the distance with the center of axis. This is the moment of inertia definition, which can be derived from the rotational kinetic energy. So the rotational kinetic energy formula is half pi omega square, and the moment of inertia formula is summation I mi ri square. So without inertia, there is no rotational kinetic energy. So thank you for everyone. I hope you can understand.